Hello everyone. Welcome to this session Azure Messaging Patterns by Clemens Vesters. Today he is joining from Germany. During this year's conference, he will be doing multiple sessions. He is also having one more session tomorrow. In today's session, he is going to talk about messaging patterns. Please welcome Clemens. Clemens, you can take over.
Thank you very much. So welcome everybody. I hope that we can have the next integrate again in person so I can see you while I'm speaking. But while things are as they are, I'll be happy to talk to you this way. We'll talk about messaging patterns and specifically about the various services that we have and how and when you should use them. Because that keeps being a question that we are being asked, and also gives me an opportunity to walk you through kind of the services from a high level and why we have them. And so that's and I'll be talking about patterns in a broader sense, kind of along the way as I talk about those things. So let me just make sure that I have the mouse in the right window. All right, so. I'll be talking about the messaging suite that we have of services. We have Service Bus, we have Event Hubs, we have Event Grid, and we have Relay. And the question is that we get posed is, why do we have all those services? And at the top level, the reason why we have those services is because they are serving different patterns. Everything started with the Relay and with Service Bus. The Relay is a service that we started as an incubation as early as 2006. And then we added Service Bus, which means the queuing capabilities in 2008. So all those things were happening way before Azure started in 2010. And then we added the today's broker technology, if you will, message broker technology in Service Bus in 2011. We started Event Hubs in 2013-14. And then Event Grid about 3-4 years ago as an extra service. And the reason why those services exist is because we had more and more requests for additional capabilities, additional features. And at some point, Service Bus which was kind of is the flagship service, if you will, that is the Swiss Army knife, and I'm going to get there, was no longer operationally the best host for particular workloads. Like, for instance, Event Hubs is enormous torrents of data with relatively little processing in the middle, very different from Service Bus. And then it eventually made sense to really have those services run as separate services. Also, what you'll notice is that the way how we charge for those services is a little different. And that's another reason, because the patterns, the usage patterns are different. The reasons for having those services are different. And so I'm going to explain in the next 40 minutes why we have those services in that detail. But as an overview, Event Grid is a service that is push. So you push events in, and then we take care of pushing those events out, and you don't have to worry about the act of pushing. If you have ever called a webhook from within your application, you will know that it's really difficult to deal with the error handling. Like, what happens if the service you push to is too busy? Event Grid takes that away from you, and it helps you with that. Service Bus is our pull cell queue-based broker. I'll talk about that more. And Event Hubs is effectively our tape drive pattern that is using highly partitioned, very high throughput telemetry service. And then the Relay is for bridging connections across firewalls. It's a bit of a different services than the service than the other ones, but I'll be talking about that as well. Before I start, let's talk about some differences in messages or in datagrams. When we move data around in Event Grid and in Service Bus and in Event Hubs, as well as in Kafka and MQ and ActiveMQ and SQS and Azure Queues and any of these services, we are dealing with different kinds of data that we're moving, and the different kinds of data have direct impact on how we need to think about architecture. if you have a job or a command that you want to go and send to another party, you're conveying an intent. You have an expectation from them. And you're often engaging in a conversation with them, which means you are sending a command and then you're expecting feedback when that command has been executed. Also, those intents typically control a transfer control from one part to the next of the system, or they actually do actual value transfers. Like if you think about a bank transfer, right? You're doing an accounting movement of money, of value from one place to the next place, and that's something that's expressed in messages. All those things are intents. If you have an intent, you're expecting processing, you're typically expecting that processing, the handling of that event by one party, which is very different of a relationship from eventing, where you're simply conveying facts. You're telling another party about things that happened in your realm, in your system, state changes, etc., and you make that information available for them to go and act on. So you give them history, you give them things that have already happened, and you have not an expectation at all about what shall happen to them. So that's the difference that we draw between jobs and commands or messaging and eventing. And so event hubs and event grid are services that are focused on the eventing side. So they're about carrying and distributing facts, and there are pub-sub services, if you will, for that purpose, so that it doesn't matter how many parties get a message. And Service Bus is a service which is focused on transferring control, transferring value, transferring jobs, and allowing a client to have enough control over a job so that we can be sure that the job gets executed. And if the job fails, that the job then gets executed eventually. So Service Bus is, so we'll talk about jobs and commands first, is the service that's specializing on this, but it can also do eventing. So the core concept of Service Bus is a queue. So you have a log, and you can put messages sequentially into that log, and then you can go and take messages from that log. What's important from a pattern perspective with a queue is that each message is handled individually. You take a message, that message gets locked by the broker. It is exclusively assigned to the owner. And then you get to do work. And once you've done the work, you know, as the receiver of that job, decide what to do with effectively the job receipt or the job order that you got. You can either say, I'm done with my work, and you're completing it. Completing the message means that you are done with that work, and the job order can be removed. The message gets removed from the broker. Or you can say, I'm going to abandon this message. I'm going to abandon the job, really. It's abandon, complete, all that nomenclature that we have in Service Bus really talks about the work that you're doing. And so you abandon the job, and then you put the message, you put the job order back into the queue from where it can then be redelivered. You can also, if you are inspecting the message, you find that message cannot be handled correctly because it's malformed. You can put that message on the side into what's called the dead letter queue. And where it can then be handled separately. And there's automatic handling. If the message shows up in your processor and the processor crashes and keeps crashing, then the message gets put back into the queue all the time, and there's a threshold, the delivery count, after which the message then automatically gets put into this queue on the side, the dead letter queue. Service Bus also allows for transactional message handling, which means you can go and take a message out of a queue, and then you can put that message into another queue, and the work results, really, the outcome of that job, into another queue. And then you can go and do the commit for sending the data on the outbound and settling the inbound job in a single atomic transaction. And if you do this, you have effectively an atomic transaction model in a cloud system. Even though we really don't have coordinated transactions in cloud systems, we can't involve the database. But message brokers are the next best replacement that exists for that. Topics are the tail of a topic, which means that the side where the messages come from, it behaves exactly like a queue in Service Bus. The topic allows you to send messages in. You can have filters on a what's called a subscription, and on that subscription, you get to select messages based on metadata. You cannot look into the payload, and that then gets assigned to an individual subscription, and then you can go and pull the messages out of those subscriptions. You can go and create routes using topics. You can go and do partitioning using topics. You can build effectively topologies of message distribution using topics. Topics are something that has been expanded. I'll talk more about Service Bus in the session tomorrow, very recently, with more capabilities. And you can also today create ad hoc subscriptions into topics. So you don't have to go and create these subscription objects anymore. You can actually go and just show up and start listening on a topic, if you will. And that's a new feature which makes that capability even more flexible than it is today. But Service Bus is effectively your Swiss Army knife for messaging-driven workloads, but it's primarily for these queue-oriented workloads. All those subscriptions on topics as well as queues always have individual message handling, and they always assume that you are processing messages individually. And once you've seen a message, once you've taken a message, you cannot go back to it. The most important feature that exists on a queue that doesn't exist on Kafka, that doesn't exist on Event Hubs, is the competing consumer model, which means you have a business process which takes a message out of a queue. I explained that. It's exclusively assigned to that party. And now another party can also take a job, and many parties can go and take jobs in parallel. And each of them can work on that on those jobs, and they can settle those messages individually and in any order that they like. Also, you can now see very easily what the progress on that queue is as the business processes are dealing with the messages. And if you find that the queue is getting longer, then you can go and trigger another business process to go and process more messages. So that's something that, for instance, Azure Functions, but also for Kubernetes, for instance, the Kata project do. They observe the message queue length through Azure Monitoring Metrics. And then if the queue length gets too long, they will go and spin up another worker automatically to provide more capacity. And then if the queue length shrinks under a particular length, then they can go and scale down that work again. So that gives you true load balancing, and none of your processes will be overwhelmed. Another characteristic is that you get offline and batching, which means you can go load data into a queue if the business process gets upgraded. So if you don't have a business process which is easy to upgrade, and you have to go and take that down, so not easy to upgrade without downtime, then you can go and take that business process down. All the messages will stay on that queue. You can bring that business process back up, and the business process will go and read the data then, but the front ends can, the submitters can still go and send messages to you. Or you can also choose to let messages queue up for a while and then only bring the business process online for a particular period of time and then shut it down again and effectively use the queue as foundation for a batch processor. And always what a queue does is it will help you with load leveling. If you have a lot of transactions, if you have spiky traffic that comes up in the front, the queue will effectively take all that punishment. It will take thousands of messages a second. And even if the business process, by average, can only do hundreds of operations per second, or even tens of operations per second, it will never be overwhelmed because it sits behind the queue and it pulls the data in. So that was Service Bus, and it's all based on having this pull pattern with individual settlement, individual handling of messages. Event Hubs is different because there the bookkeeping about the message state is not done by the broker. Event Hubs is an infrastructure that ultimately simply takes messages in and writes them into a log sequentially. And it makes them then available for consumption, but really the consumption, where that consumption happens, is really up to the client. And the client can choose to go to the oldest retained message. Event Hubs in Event Hub Standard retains messages for up to 7 days. message event hubs dedicated, or the new premium SKU that we just announced at I was about to say PDC conference, the Build conference, holds data for up to 90 days. And so you can go to the start to get the oldest events. You can go choose to only get the newest events, or you can do a time-based offset into any point in time between right now and the last 7 or 90 days, depending on how long you choose to retain that data. But that's mostly your index into that event log stream. And a client can go and read the stream again and again and again. So this bookkeeping that Service Bus does, this queue pattern and the competing consumer pattern that Service Bus has, does not apply here, because the scenario is typically different. The way how Event Hub is being used is really almost like a tape drive has been used in the past, where you're writing data down that comes in, and then you're going back to that data and you read it sequentially, like from a tape drive, to go and analyze it. So the natural partner service to go with Event Hubs, for instance, is Azure Stream Analytics, which you can attach to a stream like this, and it can go and make sense and read the events, make sense out of the stream. It can go and read those events and compute aggregates over them and produce new insights based on that event stream. Because Event Hubs also supports the Kafka protocol for producers and consumers, it can also compose with common infrastructures for stream processing like Spark and Samza and Storm and Flink and very many other stream analytics processing pipelines that are attaching with the Kafka protocol. One of the principles, because Event Hubs is much simpler than a queue is, but it's used for a much higher throughput, is that Event Hubs is typically, and a single Event Hub is typically split up into multiple partitions. In Event Hub Standard, you can have up to 32 partitions, and the way how you think about a partition is that it is an individual log that you can go and write data into, and you are choosing partition keys for events that need to stay together, and we then assign those keys to partitions. That's the architectural pattern for Event Hubs, is really to go and put streams of events into an infrastructure, and then go and read those out and read those again and again. Very often, it is used as a one-time pass-through and not necessarily a store. So the 90 days retention, even 7 days of retention, is already very long in our view. Let me explain that to you. This here is a chart that illustrates data value. Actually, it is oriented around the price that you have to pay for a data feed from a US stock market. So directly the market data feed. There's effectively two levels of data. Level 2 differs because there's just more information in that layer of data, and what you can see is that effectively only the real-time feed differs in value there. At real-time, there is a lot of value in those feeds, and you pay a lot of money. You pay tens of thousands or hundreds of thousands of dollars to have these terminals that give you real-time data, and that can also feed real-time data into your algorithmic trading processes to get trading information. And as soon as the data is a minute old, it really degrades in value, because it is now information that more and more and more people have. So you're really paying for real-time access, like the first few seconds that data is on the market, because then you can go and react, and you can go and be quicker than most other market participants. At 15 minutes, the data becomes public through various distributors. After 24 hours, kind of in that time, the data is almost worth nothing, because it's then literally public. And then it gains some value again as it gets historic. But really the core value is in real time. And that's true for a lot of the data that goes through Event Hubs and goes through these kinds of infrastructures. They're really built to go and catch a lot of data in real time, forward it in real time. And that's how they are built, and this is why the architecture looks like it looks. You have the occurrences stuff that is then expressed as events, which you capture. They go into, and that's what I call catching rain. You put them into event hubs. There might be some optional layer in the middle that goes and enriches and reduces and validates and filters, effectively takes the data out of an event hub or out of Kafka and then does some work on it and puts them into another event hub or another Kafka. But then as they're disseminated, because the data is so valuable when it's fresh, it is going into different directions at the same time. That is why we have consumer groups on event hubs. And that's why consumer groups exist on Kafka, because you want to have on that same raw, super valuable data stream, you want to have data visualization, you want to go and put some dashboards into people in front of people. You want to go and put the data into a database so it can be analyzed there, and then you want to go and run it through stream analytics in various forms of technology. And it's not rare that a single feed gets pulled into 7 different directions with different technologies because that data is so valuable. And if you think about the market data story, right, within a few seconds, that data degrades, which means you want to do as much as you can. You want to get as much value as you can out of that freshness. And that is why those infrastructures exist. It also means that those infrastructures optimized for speed don't do a lot of work. So you don't have as many features inside of event hubs as you have in Service Bus, because velocity is the thing that matters. Low latency is the thing that matters. And that's also why we're relentlessly optimizing for latency in event hubs, and specifically in event hubs premium, as we showed it around build, and that you'll hear more about this week. What we don't believe in is, we don't believe that event streams are great databases. And that's also the 7 days or 90 days limit that we put on event hubs is something that is a deliberate guidance statement, if you will. We don't think that event hubs is really made for those first few seconds in the life of an event. And very many customers use it that way. So for many customers who we have, the 24 hours, the minimal retention time, 1 day, is something that they use for the case that their consumers are falling behind or that their consumers might be down. But in reality, they only read that event per consumer group. They only read that event once, and then they project it into different stores if they retain that data. They never go back to the event hub 3 days later, 7 days later to go and pick up those events. Because as data ages, you need more indexing. So here in this picture, you have a bunch of cars, and the bunch of cars form a fleet, and that fleet might be based on very many different aspects. You might have an insurer who has these OBD boxes that are plugged into the car. You may have a vehicle manufacturer who wants to go and put telemetry, who wants to harvest telemetry from the cars that they manufactured. You may have a fleet manager who has instrumented all the cars that they manage in their fleet. There's various different reasons to do these kinds of flows, and sometimes a single car emits several different streams. Those streams go in real time through the upper path. So they're going into event hubs as the central store, but then they go and get aggregated and are being visualized or being acted upon in real time. That's all stuff that happens on that data stream, consolidated from all those vehicles within the first seconds of those events existing. And then on the lower path, you might be interested in certain technical information that's coming out of the car for historical reasons. So what you'll do is you're going to go and take the same stream or a subset of that stream, which means the technical information, and we'll go and put that into a database. But that's a different model. That's a different store. And you will go and take those events and you will enrich them with extra metadata. You will take the events, you will open them up, you will look into the payload, and you will store the payload first and foremost. And then you will go and do further indexing on that payload. Because if you store technical data and you want to do some postmortem on let's say, an engine problem that a particular car has, then you will say, hey, I have car 721215, and I've had a engine problem with it. What was the oil pressure in this particular point in time? And yes, you will be interested in getting a stream, a substream, from point in time until point in time, but you already have 3 or 4 different indexing dimensions, lookup dimensions, that are not just the time axis. And those will lead you to that substream. And event hubs or Kafka, the only index that you get is time, which means you would have to go into the event hub. You would start with effectively the point in time, and then through the entire torrent of events, you would have to go and dig through and then find the information that you want here. And that's enormously inefficient. And you have to go and read that through that entire event torrent over and over again to kind of dig out that information. And because the information doesn't change, right? Events are facts and facts don't change. It is far more effective, far more efficient to go and store the data into a proper database and then look the data up from the database and do the queries right there. Having talked about event series already, let's talk about events that are discrete. So the event series that we just talked about in event hubs are time ordered, context partitioned, and they usually give you condition information, right? There's oil pressure, or there's some diagnostics information that you're getting. You get metrics from particular services, but they're all point observations that rarely make any sense without looking at the prior and the later events, so that they need to go and hang together. And typically only the aggregates out of this are actionable. Think of a temperature sensor. If you're observing the temperature of a room, that temperature that is in that room will fluctuate around the sensor, and you will not act on the temperature going up or down 1 degree 1 second to the next, but you rather will go and calculate an average, and then you will go and act if the average goes above a certain threshold for a certain time, and so you're actioning the aggregate. That's what you're doing with event series. However, with discrete events that are representing state changes, you will typically act directly. And those are a different class of events. And that's what we call discrete events. They're independent. They have nothing to do with the prior event or the next event. Event grid is specifically an infrastructure for that. Event grid is how we provide you with events that are raised by the Azure platform. So if a storage account blob container has changes in it, a directory is being created or deleted or changed, a file is being created or deleted or changed, we will raise an event for you, and you will be able to subscribe to that event using Event Grid. If in the Azure Resource Graph, a resource changes its state or comes into being, you can go and subscribe to the resource graph, and you'll be raised an event. If you even the messaging services that we have are equipped with events, which means if there is a queue and service bus which has pending messages but nobody's reading it, it will periodically raise an event for someone to go and start reading from that queue. You can capture those events and you can handle those events using whatever Event Grid is able to call. Typically, we're calling webhooks, and more tightly integrated into the Azure platform, we're calling Azure Functions. But you can also go and send events to Service Bus. You can send events to Event Hubs, and we can also call other parts of the infrastructure. It's the focus of Event Grid is to take these discrete events, either from the platform or from you in the form of custom topics, or from a SaaS platform in the form of partner topics, and then route them to those destinations where they can go and cause extra work to happen, where you can go and extend effectively the functionality of these systems. We're basing this on a standard we have developed together in the CNCF, a Cloud Native Foundation, as a working group called Cloud Events. And the Cloud Events format that we defined there with 30 other industry partners is the foundation for what we do in Event Grid. So we're implementing the Cloud Events format, and we're also implementing the Cloud Events standardized bindings. and you'll see more and more and more infrastructures supporting cloud events that then will also easily compose with Event Grid, and already do. Event Grid exists in two forms. One is built into the Azure platform, and the other one is brand new, and that is in the form of Event Grid on Kubernetes, where on Kubernetes with Azure Arc, where you can deploy Event Grid into any Kubernetes cluster that has been enabled for Azure Arc. The way how we look at these discrete events and how you can implement things with Event Grid is that there really are an extensibility enabler. You have an event that's being raised out of the infrastructure or out of an application, and you're simply reporting out a fact that has happened in your system. And now you're able to go and create extra new functionality without the original core of the application being necessarily aware of that extension existing. That is significant. So for instance, if you have the sales lead created event that comes out of a CRM app, the CRM app is largely just a database application that is keeping track of activities in sales, or a sales application, activity in sales, and basically records them, but sometimes does things with them. But if you want to go and take action, probably tactical action based on that sales lead being created, there's a new address, and now you want to go and contact that particular person. You want to send them some particular information. You have an event or an activity that only runs this week. Then you want to go and build some functionality, and you may want to go and build this in Azure Functions very easily. And then you want to go and hook this up to the work that happens inside of that CRM system without touching that CRM system, without having to go inside of it. So if the CRM system kind of spews events out, and you can go and catch those, and you can go and act on them, it's a very easy way to go and build extensibility. So discrete events, these event engines like Event Grid, are a great way to enable extensibility for your applications. And so that's the way how we're looking at event-driven, is that you have a core service, and that core service or your microservices, they're interacting with each other with commands and requests. That's kind of service bus territory, where you are, or RPC territory, where one service is talking to the next service. And then if you want to go and extend those services further out with more functionality than has been initially designed and thought about, then you effectively extend by allowing state changes to be propagated, and then by extensions to go and react to those state changes, look back, get the necessary data related to those state changes, and then implement other completely different functionality. One more example, for instance, the Azure Blob Store is a core service of Azure, and you can go and simply by extending it with event handlers that are reacting to the blob created event, you can react to files being uploaded that have the JPEG extension. And if you are reacting to a JPEG extension having been uploaded, you can then be called, a function is called, that can go and take a look at the file, inspect it whether it's really a JPEG document, can go and read it, and can create thumbnails in a different container of the same Azure account, so that you have an automated thumbnailing service. The Blob account itself didn't know about it being a thumbnailing service, but you could easily extend it with that hook that notifies you that a new JPEG file has been uploaded, and you can build this thumbnailing technology kind of into this storage account, using the storage account's ingestion gateway, using the storage account's RBAC system, etc. But you can build functionality simply by extension. The relay is a wholly different story, and has very different uses than the core messaging services, but they compose really well. We have a lot of scenarios where there is microservices, databases, other endpoints that are sitting inside of private networks or on a public network, and they need to have integration with the cloud, and we need to be able to kind of get to them to make that for you to understand that better. Sorry, I brought a few examples. You have a cloud app, and the cloud app needs to get to a on-prem firewall asset. There's a database. The database sits on premises. You can't move that database because it's sitting there forever. It's a legacy system. It won't move. The easiest way to get to it is using the relay without creating a VPN integration, which is also complicated and expensive. And if you use the Azure Data Gateway, then you automatically are using the relay because it's kind of built into this. And the app service hybrid connections feature, where the cloud app really is built on the app service, there's an app service hybrid connection manager. If you install that, then you're also using the relay. So the relay is effectively a VPN-less way to integrate on-premises assets. What we also see that being used for is that you have a SaaS system that you're building, or you have a central system of some sorts, and you have then on-premises systems, and those on-premises systems need to be integrated into that SaaS system. So example, you have medical clinics, you have tax advisor offices, you have any kind of business that has a branch or where you have a SaaS application that is providing a cloud service for on-premises businesses, which must have, for regulatory reasons or for reasons that they really want to be in control of their data, they have on-premises assets, they have on-premises servers. So that's the scenarios where you need to have a way back, a imperative way back, right? Not a decouple as we do with the other services, but really a request response path back into the on-premises system without requiring VPN, without being able to manipulate that environment. And the relay, specifically hybrid connections and the Azure Data Gateway, provide for that. Then we have scenarios like commerce sites where you have a central on-premises systems or a central system in general that can be either or. And then you have partners. So for instance, food order and delivery, like if you think about food orders, centralized food order services, if you think about pizza chains, if you think about click and collect sales, very many transportation scenarios, the partner is not running the commerce site, and they're working with someone who runs the commerce site, but you need to get the pizza order somehow into your system. And here's a way for you to be able to go and put the pizza order into the system, get an immediate acknowledgement that that is possible, and you can do this effectively with an RPC call into the partner environment, into a pizza store, and that pizza store or whatever it is can also be in someone else's network in a mall. And without requiring a VPN, without setting up a VPN, you can go and connect out, and we can then connect back in. And then what we also see is that you have these mobile, you have on-premises applications that are requiring extension with mobile device gateways. Mobile devices obviously cannot connect directly back into, or have a hard time connecting back into the on-premises assets if people are on the road. So they need to have a bridge that sits somewhere in the cloud. And again, here the mobile device gateway is really there to talk to the web and mobile devices, and then the web and mobile devices can then talk back to the on-premises assets. And that's something where we have customers who are doing work in the medical field, where the patient data really has to be on premises due to regulation in different countries. And the gateway is really only there to create connectivity, to create an access point for the web devices in the cloud. But really the data is then also being shuttled back and forth through the relay. So as the bigger picture, we have a bunch of services: relay, event grid, service bus, event hubs. They're enabling communication, right? 3 of them are enabling communication that is asynchronous and datagram oriented. 1 of them is synchronous and stream oriented. But there's more to this. and there's very many more scenarios. For events in particular, I made this only about events, this slide, but it's applying to other messaging scenarios as well. Very many of these events originate from within applications. So we have a giant suite of 380 or now 400 adapters, which are made available through logic apps, where you can go and acquire information from those SaaS applications. So logic apps is a core part of the story. Then we have numerous different sources of events, sources of commands and jobs, which are in the field in all kinds of different devices. And that's why we have IoT Hub and our edge platforms, which are also harvesting information or ingesting all that information from the edge and from devices itself. And then we also have network embedded infrastructure, like the work that we're doing on Azure Edge with AT&T, where we're embedding information, where we're embedding services directly into the 5G network. All of those sources ultimately yield data that is being ingested into the Azure cloud using AMQP, MQTT, HTTP, or cloud events. So our principle here is to be open and to use open standards for this. And then we have, as I said, event routers, that's Event Grid and Event Log Store, where we are catching that information, but those are just means to an end, because we have very, very many services which are then ultimately event-driven. So we have stateful analysis and AI, stream analytics, HT Insights, many other services. We have dashboards and very many apps. You have Power BI as one example. Very many ways to go and index streams in databases, may that be Cosmos DB or SQL or Postgres SQL, Azure Functions, and of course, Logic Apps as a workflow engine. And then we have various ways to go and archive that information. So our story here is not one where we say it's event hubs or it's Service Bus that we're talking about. We're really talking about the eventing platform is Azure all up and not just one product. And those events take various different journeys. So one of the goals that we have is to make those event flows smoother and smoother so that you don't really have to write a lot of code to kind of make those flows work. And so you see more and more of that happening in the portal, specifically, where you can go and stitch those routes together, and you're going to see more and more of this. So ultimately, that picture then evolves into a bunch of building blocks, which then turn into this portfolio of services that we have, SaaS platform integration coming from Logic Apps, EDI integration in Logic Apps database, change capture, which is something that we do in the data platform, and more also on the eventing side, and our protocol work that we do to make sure that you're not being locked in by the work that we do here, but that you are able to also use the clients with other platforms as well. And that is what I brought you for today as an overview of streams. And now I should go and take a look at my other picture. Okay.
There's one question I left particularly for you, Clemens, at the top of the accepted list about transactions, because I figured that would take a little bit more nuance and discussion about.
Yes. Okay. Well, so has Service Bus implemented? Yes. Has Service Bus implemented two-phase commit distributed transactions for the NQ and DQ operations? Service Bus has implemented JMS transactions or local transactions around NQ and DQ operations, actually around NQ and settlement operations. We don't support two-phase commit the two-phase commit protocol. And the reason for that is very simple. There is no transaction coordinator existing that can guarantee 100% uptime in the cloud. And there's no transaction coordinator existing which can provide 100% reliability in the cloud. And if you cannot have a transaction coordinator which can be as reliable, then you also cannot build a resource manager which can play with that provider. What's also a problem is that while there is an API convention in the form of XA, there is actually no wire protocol that goes with XA that anybody could implement to work with a coordinator like this. So the most prevalent implementation of 2PC that we see today is in Java. And the interesting thing is there is that the coordination is done purely inside of effectively the Java application server, with the resource managers typically playing along using some proprietary means to enlist in that transaction coordinator, but there's no open protocol for us to implement. So there's a whole 1 hour talk about that topic, so I'm going to make that short here, but the answer is no. And the answer is we will not, because there is no technical foundation on which we can implement 2PC, and that is not even getting into the problems of the CAP theorem and the relative impossibility to keep promises in dynamic environments as in the cloud. So the second question was transactions not between queues, but between applications and the queues. You can make the enqueue and the settlement dependent on the outcome of the work of your transaction. So that's something that is possible. Obviously, like you put the commit into the queue at the end of your work, so you can create that dependency. What you can't do is you can't make a database operation directly dependent or entangle it with the outcome of the queue operation. That was answered. Individual queues and topics, access control, size limits has been answered. I think you've answered most of the other questions, right? Kevin?
At the very end of the list. Sorry, I was muted.
How can we best monitor the events for no events, failed events for different event grid topics? Add a common place for troubleshooting. How about you send me an email about this? Because I think there's more explanation required. So if you need help from us, I will happily route your questions to the appropriate people. Clemens V at Microsoft.com is my email address, or Clemens V on Twitter, and there I'll be able to address further questions. And with that, I shall say thank you very much for joining the session. And if you're interested, tomorrow I will talk about news in Service Bus.
Cove.co